Welcome, Dr. Panda. We will be starting at 3 o'clock. So that's our scheduled
Yeah,
time.
good afternoon.
Good
Okay,
afternoon.
okay, it's fine.
Yeah. Okay. Good afternoon and welcome you all to the day 2 session of the 1 week faculty development program on artificial intelligence in advanced machine learning and cloud computing, AIAMLCC 2023. So today we have on our panel an eminent speaker, Dr. Sanjay Kumar Panda, who is an assistant professor in the Department of Computer Science and Engineering at NIT Warangal, Telangana, India. He worked as an assistant professor and head of the Department of Computer Science Engineering at IIIT DM Kurnool, Andhra Pradesh, and also worked as an assistant professor in the Department of IT VSSUT Burla, Odisha. He received his PhD from IIT ISM Dhanbad, Jharkhand, India, MTech degree from NIT Rourkela, Odisha, India, and BTech degree from VSSUT Burla, Odisha, in computer science and engineering. He has 10 years of teaching and research experience in India. He received 23 awards from IEEE, Institution of Engineers India, IST, CSI, and others, which includes 2 silver medal awards for the best graduate and postgraduate in CSE, IEI Young Engineers Award, IEEE Senior Member, and CSI and ACM Distinguished Speaker Awards. He is listed in the top 2% of world scientists in a single year impact as a survey conducted by Stanford University, USA, and Elsevier in October 2022. He has published more than 120 papers in reputed journals and conferences and edited 4 books. He is a member of IEEE, Institution of Engineers India, life member of IST, and life member of CSI. His current research interests include cloud and fog computing, artificial intelligence, machine learning, and Internet of Things. He delivered more than 150 invited talks and chaired sessions in many national and international conferences. He has guided 39 BTech students, 21 MTech, MPhil, and CS scholars, and 2 PhD scholars, and is currently guiding 5 PhD scholars. His Google Scholar citations reached 24 at conferences. He also served as a guest editor in many international journals. So I would request Dr. Panda to deliver his talk. He's going to deliver his talk on osmotic computing and emerging paradigm for cloud edge and edge IoT. So over to you, sir.
Yeah, thank you very much, sir, for introducing me. First of all, let me share my screen first. I hope my screen is visible.
Yes, sir. Yes.
Yeah. So good afternoon, one and all present in this online meeting platform. I welcome all of you to this second day of this 1 week faculty development program on artificial intelligence in advanced machine learning and cloud computing. So before I start my talk, I would like to thank the organizing chair, Dr. Pinaki Pratim Acharya, professor in CSE, and Dr. Santanu Kole, professor in CSE, and program chair, Dr. Subhankar, for giving me an opportunity and invite me to this faculty program, development program, to share my experience in the field of cloud computing. So I have connected through my mobile also. So in between, if I am disconnected, please let me know through my WhatsApp number. Okay, the talk title is mentioned by the organizing chair. It is about the osmotic computing. I hope if you have not done any work in this field, then this word is new to you. In fact, very less work has done in the field of osmotic computing. So before introducing this osmotic computing, let me first introduce the title which I have mentioned for this particular talk. So you have heard about the different kind of computing paradigm. Like one is mentioned in the title of this FDP, that is about cloud computing. Before to cloud computing, you heard about several computing paradigm like parallel computing, distributed computing, cluster computing, grid computing, utility computing, and so on. So how these existing computing paradigms are related to osmotic computing? That is the first question anybody can ask if we heard this word for first time. So we'll see that where actually osmotic computing lies in comparison to the existing paradigm, and why it is essential, how it is related to the cloud computing specially. And also I mentioned in the title, it is an emerging paradigm and for cloud and edge and IoT. Nowadays, you can see our students are also very much interested to play with IoT devices, because the IoT devices are very cheap. We have several sensors. We have several real life problems. We want to solve these real life problems using IoT devices. And on the other hand, the data which is generated by IoT devices, irrespective of the application may be a healthcare application in which you want to collect the data of a patient, or it may be a problem related to smart city or smart transportation, in which you want to see the traffic in each and every location. So irrespective of the applications, these data are generally pushed to the cloud, because you know cloud is very famous to keep the data as much as possible through by providing various type of services. So one side we have IoT, another side we have cloud. One side is source of the data, another is we have to keep the data. So in between the IoT and cloud, we have also some other layers. Like if you remember a network layer, if you consider OSI ISO reference model, this model is having 7 layers, starting from physical layer to the ending with application layer. So in between these two layers, bottom to top, you can see there are several layers. Like here, you can see if you consider the bottom layer is IoT, which is nothing but the hardware devices, and the top layer is cloud, which actually nothing but the data centers, group of data sensors to provide various kind of services. In between that, we have one layer that is called as edge layer. There is another layer also in between edge and cloud. We call that as a fog layer. So basically in this lecture, I am going to tell you about 4 different layers starting from IoT, edge, fog, and cloud. So this osmotic computing paradigm plays a very important role when you see the movement from IoT devices to the edge layer, or you can say edge layer to the next higher layer, that is fog layer, or you can say fog layer to the cloud. So when you want to move your data from one layer to another layer, you can use osmotic computing. Not only movement of the data is essential, but also security is also important. But also you can say how to make a decision that whether we will migrate it to the upper layer. That type of decisions are also taken by osmotic computing. That is the reason why I want to introduce this osmotic computing in this lecture. Although you have a explicit session tomorrow related to the migration, there also you can see whatever migration you will learn in for the cloud, the same migration also you can apply among these 4 layers. So these are the topics that we are going to discuss in next 2 hours. First, I'll tell you about the relationship of osmotic computing with other computing paradigm. Like I mentioned about our fog computing, edge computing, IoT, and others. Then we'll see why such computing paradigms are popular. Why actually these are required for to solve our real life problem. In order to understand that, you first need to understand what is the difference between a monolithic architecture, then service oriented architecture, and today we talked about microservices. Although these we are using in our real life, but we do not know the background story. That's why these terms may be new to us. But earlier systems are monolithic system. Everything is done in a single place. But later point of time, in order to provide flexibility, in order to provide resilience, people have moved from monolithic architecture to service-oriented architecture. Service-oriented architecture is performing better in comparison to monolithic architecture, but still some improvements are required. Like I talked about osmotic computing, in that we need very, very small services. So that we can achieve through the microservices, or you can say ultra microservices. Again, it is smaller in comparison to the microservices. Then I'll tell you, actually we have conducted a systematic review process of osmotic computing. Like as a faculty member also, or as a PhD student, we also do some review while carry out a research work. So there is a process we have to follow if we want to go for systematic review. Review is not to collect the paper, 5-6 papers or 50-60 papers and report that in form of a report. But when you go for systematic review process, there is certain guidelines you have to follow in order to extract the paper, in order to select the paper, in order to include or exclude the paper. So we have conducted a systematic review process in the osmotic computing. And this is the first systematic review process which is available currently. You can go and search osmotic computing, a systematic review process. You can find my research work where the detailed review process is written. So I'll tell you about what kind of criteria we have considered in order to perform a survey on a systematic survey on osmotic computing. So in order to perform this systematic review process, you need to start with some research questions. Like you may have a quick question that what is the common aspect with the existing computing paradigm? One may have question that in terms of architecture, how it is different from other architecture? What unique functionality osmotic computing provides in comparison to other computing paradigms? So such type of questions you can consider as a research questions to address while you are performing a systematic review. Then coming to the next one, that is called a search strategy. You cannot arbitrarily search. Sometimes we do arbitrarily search, we type something in the Google and whatever we are getting, we accept it. But that is not the correct way for doing a searching to search a particular paper. So we have to know what are the search directories available, including the gray literature, while you are extracting the paper from the databases. Then I'll tell you about some of the selection criteria, which will help you to decide that whether a particular paper you have to include in the review process or you have to exclude in the review process. Apart from that, we have also something called as quality assessment questions. Like you got one research article related to osmotic computing, you have to decide whether to include that research article into your survey or not. So that is based upon the quality assessment questions. Quality assessment questions are also having a threshold. If the paper exceeds that particular threshold value, then we'll say that yes, it has passed the quality assessment test. So we can include that one. Similarly, we will also see some of the relevant studies, because when you do a work in a new area, you will find a lot of difficulties because that area is not a matured one. Like osmotic computing, it is not a matured one. So you have to extract the relevant studies in different forums and different magazines in order to include in your survey. So after that, we'll start another ecosystem. where you can see both cloud, edge, fog, and IoT all are together in a safe framework, so that you have a clear understanding that where actually it lies, what is the need of this particular ecosystem. Then I'll take some common characteristics to compare cloud, fog, edge, and osmotic computing. Like I can ask you whether it is supporting heterogeneity or not, whether it is providing centralized allocation or distributed allocation, whether it is executing a very small task or a large task. So such type of comparison we have to do by taking these four paradigms. That comparison we'll see. Then I'll show you certain applications of osmotic computing. Like I mentioned, healthcare is one of the application. Industry 5.0 we are talking about nowadays. Okay, that is also some of the applications. Manufacturing applications can also be possible in the osmotic computing. Then I'll tell you a very simple algorithm so that you can understand how to divide a service into ultra microservices or microservices or macro services by introducing a particular algorithm. That algorithm I call here as a task mapping algorithm. So basically this task mapping algorithm has two different pages. One is task level categorization, another is processing level categorization. Task level categorization says that what type of task is suitable in IoT layer, what type of task is suitable in the fog layer, or on the other hand you can say what kind of task can be executed in the cloud layer. On the other hand, if you go for the processing level, we check that whether a particular computational device is able to execute that particular task or not, because all layers you will get a different computational capability. Cloud case you will get very large capability. IoT case you will get a tiny processors, a very less capability, right? So we also need a processing level categorization so that we can map a task with the processing unit. So these are the things that we are going to discuss in the subsequent slides. So if you have any discussion or anything you want to clarify, you can stop me at any point of time. So let us come to the introduction to the osmotic computing. So here I have shown a roadmap. What this roadmap says, the roadmap highlights some of the major achievement in our field of computer science, starting from 1822, where we have first theoretical design of the computer system, which was developed by Charles Babbage. We done some kind of calculations there, and 2016 we have osmotic computing. So I have not covered all the milestones achieved in the field of computer science, but some of the major milestones which we have achieved in our field, that is mentioned here. So that fast computer is having very limited capability. Later point of time, people have come up with mainframe computer, but the size of the mainframe computer is very large, and processing is also very slow. So people tries to improve the mainframe computer. They want to design some electronic based computer system. So the first electronic based system is our ENIAC, which is called as electronic numerical integrator and computer. It is treated as the first electronic computer system, which was developed in 1945. But this is also having some limitations, like each and every paradigm having some limitation. That's why we are moving from one paradigm to another paradigm. So later point of time, people have developed a improved version of ENIAC, that is called as EDVAC, that is called as electronic discrete variable automatic computer. Okay, generally these computers are used for larger simulations, not simple simulations, because it is very difficult to run a simple simulation. It also takes more time. So till 1945, people have thought that how to achieve the performance of a single computer system. Like if you look into your computer system, these personal computer systems, you are only using your system. Nobody else is using your system, right? If a particular machine is allotted to you in a particular lab, then that system is only for your usage, right? It is not used by other, right? So one stage system is fully dedicated to a particular user before 1950. But after 1950, people have thought of why not go for parallel computing? Why not do two or more tasks at the same time? Like if you look into today's processor, like we have i3 processors, i5 processors, and so on. We have multiple cores. Okay, so even if we have multiple cores, if we write a sequential program, okay, we can use only one core. The other core is remain idle. So that is an example of a sequential system. So although we have a parallel computing facilities, but we are utilizing only resources of a one single system. Like if you see whatever programming language we are learning, all the programming languages are sequential only. But if you learn MP, message passing interface, parallel virtual machine, OpenMP, so these languages will provide you parallel computing facilities in which you can run multiple tasks in multiple cores. Okay, or you can create multiple threads and you can do parallel work, which will execute your entire work with minimum time. So in 1950, people come up with a parallel computing paradigm, right? So we have a parallel, you can say more than one processor in a system, or in each system we have multiple cores nowadays. So both cases we can achieve the parallelism. In 1960, we have large-scale computer system architecture, in which you can see a lot of computer systems are together can achieve a particular massive power, right? If a particular problem which cannot be solved by the help of a single computer system, if we combine multiple systems, then we can achieve it. So in 1967, we have come up with the cluster computing paradigm. Like if you see our computer lab, in our computer lab, we have, let's say, 30 computer systems, right? Let's say all 30 computer systems are having same operating system, okay, and also having same hardware and software requirements, right? So we can combine them, like each and every system is having 2 GB of RAM. Then if there are 30 systems we can achieve up to 60 GB of RAM capacity. So cluster case, what happens? We combine the systems that are having same configurations. Okay, cluster is not meant to do to combine one system with Windows operating system, another system with Linux operating system. It is for same type of system, not the different type of systems. But when you go exceed a particular number, like if you can say, I want 100 systems of the same configurations. So in your institute, you have a lab with 100 computer systems, so you can achieve it. More or less all the 100 systems are purchased at the same time. So their configuration is same. So we can combine them and we can achieve it, right? Like if a very large application is given to you, then you can decompose that large application into a smaller application, and each and every smaller application can be assigned to a particular machine. So cluster computing case, one is the cluster manager, or you can say who is managing the resources of the cluster, and the task is reached to that cluster manager. The cluster manager divide that task and give each and every smaller task to one computing system. So user is connecting to only to the cluster manager, and cluster manager only return the result after getting the result from each and every computer system, and consolidating the result, the cluster manager return the result to the user. So for user perspective, this entire system is treated as a single system image. User is not aware that behind the cluster manager, we have 30 systems or 100 systems or more than 100 systems, right? But the problem with the cluster systems is there, it is limited to a particular building, just like our local area network. Okay, but it is not giving computational priority beyond a particular range, right? Let's say in one organization we have clusters, right? But within that location only you can use the resources. That's why in 1970 people have come up with distributed computing. In distributed computing, the computers are present in different places. Like our internet is an example of a distributed system in which the computer systems are, or servers, or you can say data center in a larger term, they are not present in a single place. They are present in different part of the world. What is the advantage? The main advantage is that if there is some natural calamity happen in a particular region, it is not going to affect the other region. But if all the systems are there in a single building, if natural calamity happen or something power failure happen or some short circuit happen, the entire network is going to be collapsed. So distributed computing is having advantages over the centralized computing, but it has disadvantages too. Like clock cycle of the different systems are different. Like in present scenario, you can say like the time zone of each and every country is different, right? So managing the things becomes a challenging problem. Then till now, people have thought of the computer system which they can see in an organization. They have never thought that a computer system can also be available with user. That's why they started a non-kit personal computer, which is called as Recall-N in 1973. And subsequently, in 1974, the first personal computer was coined. The name of that personal computer is Altair. Okay, so these are personal computer that is dedicated to a particular user. Like our systems are now personal computers, right? Till 1973, they want to, if you do some kind of computations, so you have to request a particular organizations, or you have to visit the nearby organization where the mainframe computers are there or clusters are there, and you have to execute your work. Later point of time, people have come up with client-server computing systems. Server is more capable, whereas client is less powerful. Like in our computer lab also, we have a server, right? And all the computers are treated as a client. So whenever a client requires some resources, the client has to request it to the server, and server will provide the resources to the client. So the relationship between the client and server is the request response type of computing, right? So because client don't have enough power, client suppose requires some printing job, client has to request to the server, and server is holding the power, right? Computational power or a printer. The server is going to execute whatever task is given by the client. So there are multiple clients are there. They are also requesting to the server. So server maintains a particular queue in order to execute their client's job. Next, in 1988, we have internet-based distributed computing. So distributed computing can also be without internet-based, like LAN connection, you know, right? Suppose in a particular organization, you have, let's say 5 hostels, and you have connected the 5 hostels through local area network. So there is no need of internet to share a particular file. Okay, without internet also you can share a file, right or not? So people have come up with the internet-based system in 1988. Okay, here also load balancing issues are there, sharing issues are there, aggregations issues are there. So each and every computing paradigm faces a lot of issues. So as it is not possible to combine the computers of the similar nature, I cannot gather the computer, 10,000 computer systems are having similar configuration. That's why people have come up with the grid computing paradigm. In grid computing, it supports different heterogeneity, different type of task, right? Different type of machines can also be combined in order to provide the resources. So if you visit one platform that is called as VOINC, that is called as Berkeley Open Infrastructure or Network Computing. So this VOINC platform is a piece of software that you can install into your computer system. So there are a lot of projects that are running under the BOINC platform. One of the popular project under BOINC platform is called as SETI at home. SETI at home. The full form of SETI is Search for Extraterrestrial Intelligence. Okay, this is related to the space, right? So if you look into this particular project, more than 1 lakh of computer systems are live at a particular moment to provide the resources. Like you can also participate into BOINC platform. Whenever your system is idle or you are not using your system, so if it is connected or switched on, then some part of the project is going to be executed in your system. One of the another example I can give you under BOINC platform, that is called as weather forecasting. All of us are aware of weather forecasting. We are able to know the temperature of each and every place, right? Of different place. If you want to visit a place, you want to know what is the climate over there. So that project is also running under this BOINC platform. Okay, it is a voluntary project. Okay, you can participate in your system and you can see how efficiently they are executing the task in your computer system. And in 1990 also people have come up with edge computing. Edge computing is also an interesting paradigm to provide the services near to the device. Like if you look into the IoT devices and their data, let's say they are storing the data into the cloud. So cloud is very far away from the IoT devices. That's why not the services will be available around the IoT devices or near to the IoT devices so that they can provide you the better resources, right? So that's why edge computing is introduced in 1990, but later point of time it is properly utilized. So in 1998, people have come up with utility computing, like our electricity bill. You know, in summer season, you are getting, you are using fan or any air condition or cooler or some other things. Okay, so your electricity bill is more, but winter season you are not using this, so your electricity bill is less. So based upon your usage or your requirement, the electricity board is charging you some amount. Like our mobile phones also, based upon our usage or based upon our internet usage also, they are charging, right? So 1998, people have started with utility computing. Similarly, in 1999, people have come up with virtualization. Virtualization is the backbone of cloud computing, in which the same resource can be used by one or more users. Like our systems are dedicated to only one user, right? But if you see the hardware, whatever there in the data centers, the same hardware can be provided to one or more user through virtualization technology. And Web 2.0 also coming into the picture, which is also one of the technology that is used in the cloud. And people have also come up with peer-to-peer computing. Instead of client-server computing, where one is powerful, another is less powerful. So peer-to-peer computing says that each and every node in a peer-to-peer computing, they are equally powerful, right? They don't have any master-slave relations. No one is superior over others, right? They equally contribute. They may be a client, they may be a server, but they are equally contributing to a particular infrastructure. So in 2006, we have the cloud computing paradigm. Cloud computing provides virtualized resources to the customer. So if you look into the user perspective, these resources are looks like a virtualized resources, right? Like you are using your Gmail. One of the popular example I can give you, our email system Gmail provided by Google is also a cloud service, right? It is a software as a service. Out of 3 different services in the cloud, one is infrastructure as a service, platform as a service, and software as a service. Gmail is software as a service, right? So in Gmail, you know that suppose you have 10,000 emails. So these 10,000 emails are not stored in your computer system. It is stored in their Google server. So for user perspective, these emails are just like a virtual things, right? But from provider perspective, they are maintaining the infrastructure. Like they have storage. Without storage, how they will keep these emails? So they have different storage, and they are keeping our emails in their server. Right. So cloud computing becomes a very popular paradigm because based upon your usage, you have to pay. There is no need to pay when if you are not using. Like you can see, if you are not using electricity for 1 month, you are getting the bill is the base price, 100 rupees or 200 rupees, whatever may be. Right. So cloud computing becomes a very popular paradigm. In 2009, people have come up with service orientations or something called a service-oriented architecture. So service-oriented architecture is developed because you have to decompose the applications into smaller part, and you have to see that the dependency between two different models should be as minimum as possible. In fact, SUA is also one of the backbone of our cloud computing infrastructure. Then in 2012, in order to avoid the drawbacks of cloud computing, like one of the drawbacks in the cloud computing is latency. So if you want to connect IoT devices with cloud, the major difficulties you are facing is latency. Latency is nothing but delay. So in order to avoid the delay, the fog computing is introduced in between the IoT and cloud, so that the services that are provided in the cloud, the smaller version of that services can be provided by fog computing, right? So that IoT devices can achieve their requirement through the fog devices. And in 2016, the first paper was published in the field of osmotic computing. And as I mentioned, it is an emerging paradigm between the cloud edge, or you can say cloud and fog and edge and IoT. Now, if you look into the definition of osmotic computing, there is no standard definitions, but it is a related computing paradigm. Like whatever you know about IoT, you know about edge, fog, and cloud. So if a task is generated in one of the layer, if that particular layer is not capable to handle that particular task, right? So if you are generating a particular task in one of the layer, let it be IoT or edge or fog and cloud, and that particular task is not able to execute, not able to fulfill in that layer due to computational requirement, then what is next? The next step is you have to migrate to some other layer, right? So that we can fulfill the requirement of that particular task. For that region, the osmotic computing paradigm is developed. So it is providing promising solution for handling bulk of latency sensitive data generated by digital devices. Nowadays, all of us are wearing smartphones, smart watches. We are carrying smartphones. We have smart TVs. We have smart refrigerator. So these digital devices are generating a lot of data. That's why it is saying bulk data or hefty data. Okay, handling this data is not possible if you go for cloud, right? Or handling this data in that device itself, it is very difficult. Like if you talk about a particular sensor, the sensor is having a very small amount of storage. You cannot say the store, let's say a weak data in the sensor device itself. So the data need to be periodically sent to the other layers, right? So that the recent data can be stored. Like you know that also whenever we are using a mobile phone, let's say the mobile phone is having 128 GB of storage. One day will come 128 GB is going to be fully occupied. Then what you will do? You will cut this data and paste in your local drive or in an external hard disk, right? In the similar case, digital devices, whatever data they are generating, that will periodically move to some other layer. Osmotic computing also studies about deployment of the applications, especially the deployment of the microservices. It also focuses on migration of IoT to edge edge to fog, and fog to the cloud. It also studies about the optimization of application in the form of microservices. Microservices are nothing but the tiny services, very small services. I'll tell you through an example so that you can understand if you are not aware of the microservices in the next slide. So these microservices will help you, right? If there is some issues related to a particular services, right? We can easily solve that particular problem using microservices. So optimization of application can be done by the help of microservices. Also, osmotic computing paradigm promotes the digital transmissions, right? We are having a lot of data, whether the data is a sensitive data or it is a less sensitive data, or it is a very less sensitive data, or it is not at all sensitive data. That also you need to know so that you can take appropriate action in a right time. Like you can see certain type of applications like healthcare, the data are very sensitive, right? But or aeroplane system, if you see flight reservation systems, these are sensitive data. But if you talk about watching a YouTube video, if a user is watching a particular YouTube video, the data is not that much sensitive. So you have to make the task level categorization. That's why I mentioned it. Different type of tasks are generated by different applications based upon their necessity. So you have to categorize them. So some of the popular applications you can see in the osmotic computing, that is called as transportation, smart transportation system. Suppose in a particular highway, there is an accident. Okay, so you need to inform the other vehicles to not to follow the same path. Right? If you follow the same path, then it may cause huge traffic. Right? So in that case, you need to circulate the information so that if there is a diversion, okay, so they will use that diversion to avoid the traffic. There also you can use osmotic computing. We can use in the smart cities, smart transportation, education system. We can go for the smart healthcare systems as well. Like I mentioned, the patient data we are capturing. If the data goes beyond a particular range, which is specified by the healthcare professions, then immediately there is an alarm signal, or immediately there is a message will be sent to the respective person, right? So that the proper care can be taken care for that particular patient. So such applications can be achieved by the help of osmotic computing. Now, as I am talking about the microservice architecture, so I just want to show you this particular example so that you can understand what is the difference between monolithic service-oriented architecture and microservice architecture. Now, you can see in this picture is simply how you purchase an item from any e-commerce site. Let us consider Flipkart or Amazon or any site which you like to purchase. The same thing is mentioned here. Like here you can see a user, okay, has searched a variety of items and finally choose a particular item to place an order, right? So the first step, what the user is doing, the user is placing an order, whichever item he like, he put in the cart and finally paid the amount to place the order. Okay, so there is a unit or there is a microservices that is called as order service. The name of the service we say order services. Order service, the role of order service is to receive orders from the different users. So whatever order you have placed, that is redirected to the order service. Once it is reached the order services will send the order details to a module that is called as PubSub module. PubSub stands for publisher and subscriber. One of the simplest example I can say you of the PubSub model is that suppose you are liking a particular singer. So whenever you are listening a music, so you subscribe to a particular channel, right? So whenever a new video or new audio or new music is uploaded by that particular in that particular channel, then you are getting one notification. right or not? So that is called as publisher and subscriber. We are the subscriber. The owner of the channel is the publisher. So whenever the publisher publishes a particular item, then that will be notified to the user. Okay, so that's why we have a PubSub model. Once the order service received a particular order, that order is sent to the PubSub model. So the reason of sending it to PubSub model is that publisher may be one, but subscriber may be many, right? In a particular channel, the subscriber may be many. So once we get the order, simultaneously we have to start other works. Like somebody can say, we have to first check that whether the payment is successful or not. Okay, once the payment is successful, then only you are going to see the particular item, right? Another person case that will send to our warehouse to check that whether that particular product is available in X warehouse or not. Otherwise, you will go for Y warehouse, Z warehouse. Like e-commerce sites, they have also a different warehouse. One may be at Kolkata and maybe in Delhi, another may be at Mumbai, another may be at Hyderabad, and some other places also, right? So we have to check in our warehouse whether that product is available or not. So once this PubSub module receives the order details, so it is sending that to the packaging service. Okay. So order event is received. It is sending the details to the packaging service. So packaging unit is going to prepare it for shipping, right? And once order is packed, it will be again informed to the PubSub module. Then the PubSub module will inform the shipping services that the product is packed and you need to deliver it. And in each and every step, there is a unit that is called as notification services. Okay, when the order is packed or when the order is shipped, when the order is near to your hub, every information will be informed to the user through this notification services, right? So nowadays also early days they are using different kind of courier services, but nowadays e-commerce websites are having their own carrier, right, for delivering the products. So what you can see in this example, each and every component is dependent on each other. Okay, so if you go for monolithic system, the entire system is treated as a single system. So in that system, if let's say the packaging services is not available, okay, then the entire network is going to be collapsed, right? Or shipping services is not available. Like COVID-19 time, we have seen that some of the some of the essential items, other items are not delayed or they are not reached to the customer in time. So in that case, if you see, the entire network is going to be collapsed. So in order to avoid that, we start the microservices. So here you can see there are 4 different microservices we have. One is order, another is packaging unit, another is shipping unit, another is notification unit. You can go beyond these 4 services, not mandatory you will go for 4 different services. As much as you can decompose, that is a better way to handle the services. So what you can understand in this picture, that microservices enable you to break down a very large applications, that is placing an order to deliver a particular product. So that is a very large application that we break down into smaller independent services. The reason of dividing it into smaller independent services is that if a service is not available, then only that particular component we need to recover, right? Not the entire system. But monolithic system case, you have to, the entire network is going to be collapsed because every components are very tightly coupled with each other. But microservices case, it is loosely coupled. So we are only concentrating on the microservice, that particular microservices, and other microservices are well and good, right? So this is the basic difference between the monolithic system and microservices. Now, in between this monolithic and microservices, I also told you another term that is called a service-oriented architecture. So you may ask, what is the difference between, again, monolithic with the SOA or SOA with microservices? So let us see. So here you can see SOA is in between the monolithic services and microservices. If you compare service-oriented architecture with microservices, service-oriented architecture is coarse-grained and microservices fine-grained. What is the difference? You can ask again the coarse-grained and fine-grained. Suppose somebody will ask you, there is while you are filling a application form, okay, somebody is asking you write the address. So in that address you are writing your parents' name, then you are writing your street name, you are writing let's say in the district name, state name, pin code and everything into a single field. Okay, so if every user is writing the entire thing in a single field, and if I want to generate a query by saying that find the pin code of all the candidates, it is very difficult because everything is captured in a single field. So segregating these informations is very difficult, right? Although you can say the pin code is 6 digit, if somebody is writing 4 digit or 3 digit or 7 digit, 5 digit, everything is going to be acceptable because nobody is validating that particular field. But if you go for fine grain, we have multiple fields. Suppose in the first field, I'll ask you, what is your parents' name? Second field, I'll ask you about your street name. Third field, I'm asking you to select a district, state or country and pin code in different field. So in comparison to the previous one, second case, the storage requirement is more, right? But then the previous one, the storage requirement is less because the entire thing you are capturing through a single field. But if you capture as a fine grain, the advantages is that any type of information you are asking. Suppose I'll ask you that out of these applications which apply, whoever is applied to a particular application, okay, or particular post, find their district. So you can easily find their state, you can easily find, right? So that is our fine grained approach, right? Fine grained means you can say much detailed approach. So although monolithic system is a large system where you have a single code base, but that is decomposed in the SOA and that is further decomposed in the microservices. So service oriented architecture, service modules interact with one another to carry out the specific business objectives. You can say like you are saying packaging. Packaging also, let's say different parts. Let's say inside the product we are doing one type of packaging, outside the product another type of packaging. So one particular module which you have identified in SOA that can be further decomposed in the microservices, right? Now here you can see as we are talking about the cloud computing, right? Cloud computing provides enough computation power. So if you go for cloud-based task taxonomy, because different kind of tasks are generated by different devices and different layers are handling them different way. So overall, the task is of two types. One is called a short running task, another is called as long running task. Like there may be a smaller task that need to be executed in a particular period. Again, it may be periodic, it may be an aperiodic also. On the other hand, there is a very large task that need to be executed, which may take more than one day. So we can divide the task into short running task, and this is long running task. Because long running task is not going to be fulfilled in the edge layer or fog layer. It will be go to the cloud. But when it is a short running task, although it can be executed in the cloud, but it takes more latency. That can be used in the below layers instead of pushing everything into the cloud. Now, if you go for short running tasks, it is again two types. It may be high performance computing task or it may be data intensive task. Similarly, long running task, it may be interactive task or it may be compute intensive task. So here you can see the different type of intensive task we are saying, whether it is a compute extensive or it is a data intensive, sometimes we say memory intensive. Like sometimes you can see a particular application where storage is the primary requirement. We don't want to process it. We want to keep them in a safe storage, right? So that multiple copies of the storage can be provided to different users. Like YouTube is one of the medium, right? Where we keep everything into every music, each and every music in storage. And whenever a user search, if the keyword matches, then the corresponding music will be played, right? So that is storage intensive, right? So that we focus more on the storage rather than the computations. So if a task is compute intensive, it means that it requires large computation power. Like I told you about weather forecasting. In weather forecasting, what happens? There, you need large computations. You have data, large data, but you have to compute it. You have to apply different artificial intelligence, machine learning models. Okay, you have to train a model. You have to predict something. So you need a large computations. Such type of task is called as compute intensive task. Sometimes in order to process something, you require large amount of memory, or as I said, storage. So such tasks are called as memory or storage intensive task. And as we are talking about AI and ML, you know, or deep learning, in which we are dealing with a very large amount of storage data, right? The data size, sometimes it is more than 10 TB also. Okay, processing such data is really challenging. So such type of data set, if you are dealing with, we call that as a data intensive task. The reason of dividing the task into multiple categories is that we have to find an appropriate resources for each and every task. Okay, a resource may be capable to handle small tasks as well as large tasks, but there are some resources which can execute small tasks. They cannot execute large tasks. So you have to do proper segregations so that intended things can only be provided. Okay, intended resources can be provided to the respective one. That will be more helpful. Okay, so here you can think about GPU systems as well as CPU systems. Okay, as we are talking about large computation power, sometimes we deal with the GPUs, in which you have more arithmetic logic units. Okay, but the CPU case, you can see the computation is limited. That also you can do in order to do faster processing. Now, the problem with cloud computing infrastructure is that with the outburst of data generated by digital devices, so imagine that if you look into the IoT statistics, you will see Cisco predicts that this much billion of devices are going to be connected by 2030. Or some other reputed organization like International Data Corporations, they also predict that by 2030 or 2050, these many devices are going to be connected to each other, right? So if such a thing happens, and if you want to keep the data and devices both in the same unit, it is very, very difficult. Alternatively, you can say interaction between the data and devices becomes difficult. Okay, and it is also not possible to push all the data to the cloud, because you know data centers are storing our data. The main data, whatever data we have, if you are using Google Drive or OneDrive or Gmail, or you can say Facebook, all the data are stored in the data centers. And these data centers are placed in a particular location, like geographically centralized data centers. They are, that is, the data centers are geographically distributed all over the world to store the data. But the problem is that it is not necessary that the distance between the user device and the data center. Okay, we are not looking into the physical distance, but the communication between the IoT devices, and if you look into the data center, if it is very far, then it is going to be impact on the quality of experience, right? Like whenever the signal is not good, so whenever you are watching a video, the video is paused, sometimes the video is blurred, right? So it will impact the quality of experience. Okay, why it occurs? Because the devices are not the computational or the storage, or you can say data intensive. These things are not, resources are not available near to the user. So the performance is not good, and the distance between the data and devices leads to delay the entire process. So as the solutions, what happen? These computational powers need to be available near to the user. That's why the fog and edge computing paradigms are introduced in the literature. But one important thing I would like to mention here is that although fog computing is available near to the customer devices or digital devices, it is not going to replace the cloud, because the computational capacity provided by the cloud is much higher than the fog. Okay, that's why if it is a long running job, then ultimately it is going to the cloud. But if it is a short running job or in between short and long running job, then there is a chance that we can execute that in the fog. So fog is not going to replace the cloud, rather than it is providing a complementary services on behalf of the cloud. Okay, by providing resources near to the digital devices. So fog computing paradigm is introduced. So as the data centers are centralized and they are placed in different places. Okay, like if you look into our country, we have only one data center. If you talk about, let's say, if you talk about our Amazon Web Services, so we have a data center at Mumbai region. So very soon they are going to make Hyderabad region is operational. So in our country, we have only two data centers. If you see, one is Mumbai, another is Hyderabad. So any request you are generating, even if you are looking the nearest data center, it will go to either to Mumbai or to the Hyderabad. That's why if there are some other countries are there where the data center is also not there. So you will get a performance degradation, also you will get a delay. Sometimes if there is a deadline for your task, then there may be a high chance that that task is going to miss the deadline. So in order to avoid that, we have fog computing paradigm. So that latency requirement can also be fulfilled with less latency. Okay, latency will be there irrespective of the system. It may be in microsecond, or it may be in nanosecond or picosecond, right? But handling very large amount of data where you have deadline, basically the real-time tasks are having deadline, right? Like aeroplane system, I told you, healthcare system. So these are having some real-time tasks, right? The real-time tasks need to be executed without latency or minimum latency. That can be provided by the fog computing paradigm. Some of the examples of fog computing, you can say the smartphones which we are using, or we have switches, we have routers. So they can provide you immediate response, okay, without any delay. So they can be treated as the fog devices. It was introduced in 2012 by Cisco. Now, people also use fog and edge alternatively. If you go to literature, you can find fog and edge. These are used interchangeably. But this picture will give you the difference between fog and edge computing. Like here you can see I have given 4 different layers. In the bottom layer, you have IoT sensors and controllers. Like you have taken a, let's say, soil moisture sensor, and there is a controller, like it is connected to a pump, right? When the soil moisture sensor is beyond a particular limit, then we start the pump. So all IoT sensors and controllers are there in one layer, right? They are connected to the next layer, that is called as edge layer. So suppose a task is generated by IoT layer, okay, or the sensors, okay. Once the task is generated, suppose we feel that that particular task cannot be executed in that device. Like your smartphone is capturing your SpO2, blood pressure, other parameters, but it is not retaining your data which you have sensed 1 year back. That's why sometimes it is saying that you have to connect with your smartphone to get the latest statistics, okay, get the historical data, right? So If the task is not able to solve in the IoT layer, then the task is migrated to the edge layer, right? And even if edge layer is also having some computational limitations, every layer is having computational limitation. Edge, because IoT layers are having computational requirement, we are sending to edge layer. If there is a requirement which cannot be fulfilled in the edge layer, then we can go for fog layer, right? If we cannot execute in the fog layer, finally we'll go for cloud layer. But earlier what we are doing, we are connecting the IoT with directly with the cloud layer, which leads to the latency issues. So in order to avoid that, we introduce two different layers in between IoT and cloud. So edge computing emphasizes processing information locally to enable decision making instantly. So you can see if your problem is solved in the edge layer, so immediately the result is going to be returned to the IoT devices. Suppose the IoT device has requested something to this edge layer, okay, and edge layer can execute it. Edge layer has completed its execution and return the result to the IoT layer. So the decision making is very quick. But if you send the same thing to the cloud, right, the distance is again the distance is more, right? So again, cloud will do the processing. Once cloud is doing the processing, again, it will send the result to the corresponding IoT device. So this will increase the delay. So edge computing also provides, you can see, a communication between the cloud systems and the edge devices. So IoT devices are also, as it is available near to the edge computing, we call that the edge devices. And there are several opportunities we have, like we can process multi-tenant, distributed multi-tenant environment. So multi-tenant means it's the same piece of software that can fulfill multiple customer requests. Okay, like you have installed something in the server, and the same copy can be used in the different computer systems. So in that case, we can go for the edge computing can solve the problem, right? And also one of the advantages is called as location-based content delivery. Suppose you have requested a particular YouTube video, right? Suppose that YouTube video is not available in the edge layer. So edge is requesting to, let's say, fog layer. In the fog layer, let's say that video is available. Then fog is giving a copy of that video to edge layer. But in your region only, another person has requested the same video. So now the edge layer is not going to connect to the fog layer because the same data is available in the edge layer. So a piece of the data which is given to you, the same piece can also be given to another region. Like sometimes some viral videos are coming. So in a particular region, many people want to watch that particular video. So that can be provided through location-based content delivery, which can be done using edge computing paradigm. Now coming to the next paradigm, which I told you in the beginning, that is called as osmotic computing. So you can see in this diagram, the innermost circle represents the cloud. So you have different types of cloud. Cloud is divided different types based upon different characteristics. So if you want to categorize the cloud based on its deployment, so it may be a public cloud, it may be a private cloud, it may be a community cloud, or it may be a hybrid cloud, right? So here you can see we have represented public and private cloud. So in the future, one cloud is going to collaborate with other cloud due to scarcity of the resources, right? So innermost layer is called the cloud layer. Next to the cloud layer, we have edge layer, and next to the edge layer, we have various type of devices. Okay, router is a device, or mouse is a device, smartwatch is a device, Arduino kit is a device, Raspberry Pi kit is also one of the device. So what osmotic computing actually doing here, it focuses on systematic service allocation using the key principle of osmosis phenomenon in chemistry. So the word osmotic came from osmosis. Osmosis is a very popular word that is used in the field of chemistry, not in the field of computer science. If you ask your chemistry friend, if you ask your friend, chemistry friend related to osmosis, they are very aware of this term osmosis. Osmotic computing is also managing resources and solving the data issues in IoT as well as in data science. So what is the main objective of osmotic computing? You can see it is available here in this circle in between cloud and edge. It is also available here in between edge and IoT. So whenever you are moving from one layer to another layer, the decision will be taken by osmotic computing paradigm, right? So there is a manager which we call as a osmotic task manager, or irrespective of that, you can say only manager. So the manager has to take a decision whether the generated task is going to execute in the IoT layer or the edge layer. Okay, here I am showing you IoT, edge and cloud. In the previous slide, I told you about IoT, edge, fog and cloud. So it can be both, right? So if the task is again not executed at the edge, the osmotic is again taking a decision to migrate from the edge to cloud. So the main goal of osmotic computing is to balance the load. So if the load is, let's say the IoT devices are heavily loaded and edge layer is less loaded, so it is going to balance the load among IoT layer as well as edge layer. Again, edge layer and cloud layer, if there is a balancing issues, that can also be done by the osmotic layer. So the next goal of osmotic computing is to make proper utilization of the resources. So utilization of resources is not done in a one directional manner. That is IoT followed by edge followed by cloud. It can be also done cloud to edge and IoT. That is in another way. So in bidirectional way, we can manage the resources in order to achieve better resource utilization. Now, as I said, we have conducted a systematic review, very short span of time. I'll tell you how to conduct a systematic review process in any topic. So if you want to do in systematic review in your respective domain, you have to focus on 5 things. So these 5 terms you have to follow in order to perform a systematic review. You cannot select any paper randomly. First one is called as framing well-defined research questions. So if you want to perform a survey, first you have to identify what are the research questions that you are going to address in your survey. Second is you have to develop different research strategies. Third is you have to define some selection criteria to select some paper or to exclude some papers. Then you have to go for assessing quality of the studies, or you can say quality assessment questions. If the score is above the quality assessment questions, then you have to accept it or you have to reject it. The next one is you have to extract relevant studies based on the selection criteria. So let us see how actually it goes with respect to osmotic computing. So these are the 5 questions, research questions we introduced as a part of survey. First is, what are the distinct aspects of osmotic computing? So any new paradigm is coming, first you will ask what are the different aspects. Okay, without knowing the different aspect, you cannot choose a particular application. So that is our first research question. The second question is how osmotic is comparatively different from other computing paradigms. Especially here we focus on cloud, fog and edge. What are the similarity? What are the difference? Whether the same application which is addressed in these 3 paradigms, cloud, fog and edge, can also be addressed by osmotic or not. That type of question can be asked as a resource questions. Next one is which applications followed the significant principle of osmotic computing. Okay, so there are numerous applications are there, right? Like I mentioned you about smart city application, industry 4.0, smart transportations, healthcare applications. These are some of the applications. But you can also ask whether we can use it in agriculture or not, whether we can use it in your respective domain or not, right? The fourth resource question addresses which key topics are already addressed in osmotic computing. That is roadmap of osmotic computing. I showed you the roadmap of computing paradigm, but you can also go for the roadmap of osmotic computing to say that which area is addressed and which area is yet to address. The last question is, what is the maturity level of the key topics in osmotic computing? Although some of the topics are addressed, but what about their maturity, right? Whether the sufficient development has done in that topic, or some more development can also be done, more improvement can also be done, that also you can think. So these are some of the search strategies we have used. We have searched the keyword, that is osmotic computing, with respect to some other keywords like osmotic computing application, osmotic computing usage, osmotic computing challenges, osmotic computing issues, and osmotic computing concerns. Because whenever you are searching, some of the other terms also you need to include, right? People generally give title osmotic computing applications, osmotic computing paradigm, or issues and challenges of this particular field. So that's why we search these things in different directory like ACM Digital Library, IEEE Explore, Science Direct, Springer Link, Wiley Online Library, and 2 Grey Literature, that is our archive. Nowadays, people want to publish preprints in the archive and also in the Google Scholar. Okay, so after going through these are the after retrieving the research papers in these different directories, we found sufficient number of papers, right? As this field is new and we got very less number of papers, the number is not a very big number. I'll tell you the numbers in the upcoming slide. Then we have applied different selection criteria, or on the other hand, you can say exclusion criteria. How to accept it, how to reject it. First, we have seen there are some articles are there that do not consider osmotic computing as fundamental study, right? Like you can see, I told you in chemistry people have used also osmosis. So you will see as they are synonyms to each other. So that papers are also going to come. So we have excluded those papers. Next one is the article which concerned with other computing paradigm, not osmotic. They considered cloud, edge, and fog, but not osmotic. Okay, but as it is a related paradigm, some research queries are going, some papers are also going to come, so that you have to exclude it. Next is the article which is written in different from English. Nowadays also many people publish in their local languages, right? And some articles are there whose full text is not available. Okay, as per the accessibility given to us in different institutes, so we have excluded it. And we also found there are some editorial notes, some summaries, some comments, discussions, blogs, okay, reviews, readers' letters, okay, preface, that also we have excluded. Then coming to the quality assessment questions. So for each and every paper, in order to include that into the survey, you have to focus on 5 different quality assessment questions. First one, did the article fulfill the purpose of the research? That you have to decide. Your evaluation may be different from my evaluation. My evaluation different from any other person's evaluation. So for each and every paper, you have to rate these 5 questions either 1 or 0.5 or 0. If you satisfy the purpose of the research, you put 1. If you partially satisfy, you put 0.5. If you are not satisfied, then you put 0. Similarly, the quality assessment questions 2 says that, did the article cover the furnished research questions issues? We introduced 5 research questions, whether they are inclined with these 5 research questions or not. Based upon that, you have to rate. Next is, did the authors satisfactorily conduct the literature review? Like whether they focused on the same area or not, whether they have solved heterogeneity problem, or they solved migration problem, or they solved a particular applications, that also you have to look into. Then next question says that, did the article present future research directions? Okay, every article we are writing, what are the scopes if somebody reads this article and want to extend it. The next question is, did the authors consider all the important things related to osmotic computing, right? So based upon that, we have evaluated each and every article which we found in our search strategy. So those studies got minimum of cumulative score of 3. That is going to be included as a part of our survey. Others are going to be discarded. And once we got this one, we have divided the work into 3 parts. One is either the article is an initial work, or it is showing a framework or model or middleware, or it is showing a use case or application or prototype, right? So this is the complete study. You can see initially we got 99 articles from different databases and grey literature. And based upon the title based selection, whether the title focuses on osmotic computing or not, so we have excluded 33 articles. So then we have looked into articles after duplication removal. Like when you go for different directory, you can find the same article available in more than one directory. So such articles we have also excluded. Then based after reading the abstract, also we have removed some article. After reading the full text, also we have removed some articles. So finally, the survey is conducted using 29 research articles. Okay, now coming to the next point of discussion, that is called as osmotic computing ecosystem. So here you can see, like why we are coming to the osmotic computing, because we know that the IoT applications require latency sensitive solutions, delay tolerant solutions, right? Without any delay sensitive solutions, right? Or even if there is a delay, so it should be minimum delay, right? It should not be a rigid delay, right? It should not exceed a particular limit also, right? Also, you know that IoT applications are having less battery power. They don't have enough, like if you talk about a sensor, the sensor is having some joule of energy, right? Once that energy is done, the sensor is going to die. Like our smartwatch also, you can see, you have to charge your smartwatch, let's say once in a week or once in a month, right? And also the bandwidth is also one of the constant. So osmotic computing provides a federated environment to manage cloud and edge data center. So sometimes we call this the micro data centers. Micro data centers are available in the edge layer, and cloud data center is there in the cloud layer. Micro data center is having less capable in comparison to the cloud data center. And you can see the applications in osmotic computing are decomposed into smaller services, that is microservices. We already discussed this one. Microservices are loosely coupled system. They are not dependent on each other. They are lightweight. They are resilient. Resilient means if a particular service is down, that service is going to be recovered. Other services will flow as it is. They are not going to be impacted. So even if there is a fault happen, that is not going to impact the performance. Next one is fine grained. We have seen also SOA architecture is coarse grained, right? But microservices are fine grained, and we can deploy microservices independently. That's why the applications which are rely on the microservices, there we can use the osmotic computing paradigm. And you know, in osmotic computing paradigm, we improve the modularity. And if you see the dependency between two different modules, the dependency is as minimum as possible. Okay, that's why inside the module, the relations is very tight. That is called as increasing cohesion. And between two different modules, the dependency is very low. So which we call as decreased coupling. So we have seen also always a desired model should have high cohesion and low coupling. Now, if you look into osmotic computing ecosystem, there are 5 different components. The first component is called a solute. Second is called a solvent. Third one is solution. Fourth one is called a semi-permeable membrane, or also we call it software defined membrane. Fourth one is called as concentration. Like this is example we know from our childhood. Like if you take a glass of water, if you put 1 spoon of salt or 1 spoon of sugar, then you will see it is going to be dissolved, right? After let's say a period of time, right? But if you put excessive amount of salt or excessive amount of sugar, then what will happen? So it is not going to dissolve. That's why solute is a dissolvable component, just like salt. And solvent is nothing but our water, which dissolves the solute, right? So the ratio between the salt to water, okay, that is solute to solvent, is called as concentration. Okay, and the mixing of these two is called as solution. And in between these two, we have a semi-permeable membrane. What the membrane is going to do? The membrane has to do the process of load balancing. The membrane is also going to do the efficient utilization of the resources. Okay. Now, if you look into this figure, the idea will be more clear. So assume that we have 3 layers. I am not showing you as a here fog layer. So we have IoT edge, another we have edge cloud, right? So here you can see there are 2 types of symbol. One is diamond, another is hexagon. Hexagon is called as solute. Solute means you can say this hexagon is called as solute. So solute means let's say salt. I am taking salt, or you can take sugar. This diamond is called a solvent, so which is nothing but water. So if you look into this figure, what it says that water is more. You can see there are less hexagons are there, but more diamonds are there, right? So salt is less, water is more. But if you look into this particular figure here, if you see hexagons are more and your diamond is less. Okay, that means salt is more and water is less. So always remember, when such a situation is there, sometimes you need a resource requirement in IoT layer, sometimes you require resource requirement in fog layer or edge layer, or sometimes in the cloud layer also. So always the movement happens between low solute concentration to high solute concentration, or it is also in between high solvent concentration to low solvent concentration. So our objective is to balance the load between cloud and edge, as well as edge and IoT. So what these are non-technical terms, right? This is the concept of osmosis, which is there in the chemistry. How it is related to our computing paradigm? So here the salt is nothing but processing time. Okay, or it can be considered as a load, or can be considered as power, energy, anything. Where solvent is nothing but your applications, microservices and services. Okay, so solvent means here you can see this diamond symbols are called as solvent. So applications are more. You can see these are applications, right? Applications are more, but processing such application, you have less processing devices or computation. What you will do? You have to move to the position where the processing requirement is available. That's why there is a movement from low solute to high solute, or high solvent to low solvent. So this is called a semi-permeable membrane. So this membrane actually takes a decision whether to move from low solute to high solute, or high solvent to low solvent, or how much it is going to move, that will be decided by this semi-permeable membrane. Also, it is called a software-defined membrane. Okay, that is nothing but movement of solvent across the solution to maintain the balanced concentration with respect to the solute. Now, this is the basic concept of osmotic. Now, if you look into the diffusion of solvent molecules, right? So I told you about solute, I told you about solvent, I told you about concentrations of solutions, right? So a region of higher solvent concentration to lower solvent concentration, or lower solute to higher solute concentration, that we have seen in the previous one. So this process, if you are moving from one layer to another layer, this is an example of migration. What we are doing in migration? Migration means moving from one layer to another layer. So migration can be done in IoT to edge or edge to our cloud. So at that particular moment, osmotic takes a primary role. Osmotic takes a decision that is whether to migrate from one layer to another layer or not. And it is not from one. It is not from one side. It is from bi-directional, right? Sometimes there is a requirement of edge, which can be also executed by IoT devices. So we migrate across cloud data center and edge devices through this osmotic membrane. Now, these are some of the research areas that if you are interested, maybe in next 5 years, the term cloud computing is not that much popular. Osmotic computing may be one of the popular paradigm. So you should know that what are the research areas that you can focus in order to carry out further work. First one is highly distributed and federated environment for automatic deployment of microservices. Like we have taken the example of e-commerce services, in which I told you there are 4 different services: ordering, packaging, notification, shipping. These are the services. So the environment which we are working here, it is completely a distributed environment. It is not a centralized environment. Although it is a distributed environment, but these components are work in a federated approach, combined approach. So we have to look into that in such an environment, how we can deploy the microservices. If you can deploy the microservices, and let's say multi-tenant applications you are deploying, so the same application will be used by multiple customers. So there are deployment issues are there. Okay, how to coordinate also, that is also one of the important. So that are the major issues you will face if you choose the first topic. Second one says that seamless co-location of cloud and edge for service migration. I told you migration may be any layer to any layer, right? So if you are migrating, its associate file also needs to be available there, right? It's a temporary files or image files, whatever you have created. Otherwise, it will not able to process the thing in that layer. So how you are going to locate them, co-locate them from one location to another location? That may be one of the major area. Third one is tunable configuration of resource utilization based on application requirement and resource availability. Always we want to achieve the resource utilization which is close to 100%, right? Until unless a application has limitation, our objective is to reach to the 100%. So how will tune for a particular application? Suppose you are dealing with a healthcare application, what resource utilization you want to achieve? If you are dealing with the smart manufacturing applications, what is your expectation? Okay, whether the resource is available or not. So how to tune such things, some parameters, or you can say hyperparameters, whenever there is a requirement, right? Fourth one is controlling and managing service heterogeneity. There are different computation power available in different layer. In fact, in each and every layer, each and every devices are having different computational capability. So managing such thing requires some kind of scheduling algorithms. The scheduling algorithm will determine whether X resource is better or Y resource is better, whether they are in the same layer or different layer. So managing that is also one of the challenging tasks. Next one is reduction in latency and energy consumption. Nowadays, irrespective of the area, people focuses on the energy, because energy consumptions also leads to, you can say, the primary requirement is that carbon dioxide is generated. It also leads to greenhouse effect. So in order to avoid that, we look into how we are going to manage the resources with minimum consumption of energy, so that we can safeguard our environment. So here you can see the difference between the osmotic computing and other computing paradigms such as cloud computing, fog, edge, and osmotic computing. So here you can see cloud computing. If you look into the data center, then the data center is placed in a particular location. So its architecture is a centralized architecture, right? But if you look into fog or edge or osmotic computing, it is a decentralized architecture, or you can say distributed architecture. Distributed means it is not located in one place, and osmotic is also a part of distributed computing architecture. If you look into proximity, okay, proximity means it is closeness, right? So cloud computing is very away from the end user, but if you look into edge, it is very close, and fog is relatively close to the end user. But osmotic case, whether you are talking osmotic in between edge and IoT or cloud and edge, based upon that, you can determine what is the proximity of osmotic computing. And looking into application type, cloud applications are latency tolerant. If there is also a little bit delay, it is going to be managed. But fog computing applications are latency sensitive. They are very sensitive to the delay. If delay happen, then it may lead to catastrophic effect also. But osmotic it is completely real time. Real time means it is also type of latency sensitive applications, or very latency sensitive applications, time critical applications. Similarly, here you can see data processing case. The cloud computing manages the data center, which is remotely accessed. But fog case, we are in the edge of the network, or edge computing, we have different edge devices, and osmotic is in between edge and cloud. Similarly, you can see other classifications like hardware case. You can see we are using micro data center in the case of osmotic computing, but cloud case you have very large data centers. Edge case you have, you can say, little bit more in comparison to micro, like you can say macro data centers are there. And a delay case, you can say osmotic computing is less delay in comparison to other. Scalability case, if you look, it is highly scalable like a cloud. Computing capability is also high in the case of osmotic computing. Storage is also high, and resource availability is high. Responsiveness is also high, like edge computing, or you can say fog computing paradigm. Data traffic is also high. Bandwidth conservation is also high. Fault tolerance aspect, it is also well managing because it is using microservices, so it is providing resilient feature, so it is high. Security requirement is also high, but cloud case the security requirement is low. Similarly, power consumption case also osmotic computing is low. So if you compare to other computing paradigm in terms of these characteristics, you will find osmotic computing is a better computing paradigm in comparison to other computing paradigm. Next, there is another important concept we want to see here, that is called as osmotic element. So like we are dealing with different kind of applications. So if you deal with IoT applications, which is in a federated and distributed environment, you want to deploy IoT applications. So they are actually represented in a graph of micro element. Micro element means, let's say like microservices, we have micro element. Generally, micro element is decomposed into two parts. One is called as service, and another is called as data. Okay, so these micro elements are called as MEL. So each and every MEL is having two parts. One is called as data, another is called as service. So I told you in monolithic system, this data and services are binded to one single code base. But if you go for microservices, these are two different parts. Like here you can see we have data.
So there is a disconnection actually with the network.
Yeah, I'm sorry, actually I was disconnected.
Yeah, sir. Okay, sir.
Yeah.
Please
So
continue.
I told here we have seen that we have micro element. So the micro element is divided into the data part and service part, right? But in monolithic system, as I said, the data and services they are combined together into a single code base. But in the micro element case, it is separated. Again, the data key can be generated during the operational phase, or the data can also be given by the user. Okay, based upon that, they are divided into either operational data or user data. And similarly, if you go for microservices, services case also, we can have operational services or we have user services. But irrespective of the thing, what I want to tell you here, in osmotic computing case, it is completely bidirectional. So this data that is flow in both directions, starting from IoT to the cloud or cloud to the IoT, right? So it characterizes bidirectional flow for domain-specific data across the IoT devices. One of the applications you can see here, like here also you can see there are three different layer. One is cloud, edge, and IoT. Here, suppose we represent different micro elements in different type of symbol. We used circle to represent cloud micro element. We used a triangle for edge micro element. We have used square for IoT micro element. So we are more interested into the layer edge and IoT, and we are more interested in the layer that is edge and cloud, or cloud and edge. So if you look into this cloud and edge, this particular layer, if you see, you can see also this dotted one represents the semi-permeable membrane. So you can see the triangles. If you look into the triangle, it is 4, okay, and it is here. If you look into the circle, it is 2. What it indicates? It indicates that the load on the edge layer is more in comparison to the cloud layer. So you can see the arrow mark. So some of the load from the edge layer is going to be migrated to the cloud. On the other hand, if you look into this edge and IoT, and this is our semi-permeable membrane, here you can see IoT devices are having more load. You can see more square in comparison to the triangle. So some of the loads of the IoT is going to be migrated to the edge. Okay. So the migration of micro element can be done between edge to the cloud or it between the IoT to the edge. On the other hand, you can see here in this case, here the cloud is having a lot of load. So it can share also some of the loads to the edge layer, or edge can also share some of the loads to the IoT layer, right? So that is nothing but the migration of micro element from cloud to edge and edge to the cloud. So this is possible by the help of osmotic membrane. So when you want to design some kind of algorithms, you have to focus on this semi-permeable membrane, which is actually going to take a decision whether to migrate in one direction or other direction. Also, it is going to provide you different security mechanisms also. You cannot migrate all type of applications. Sometimes some malicious user also inject some kind of applications to harm the system, harm the ecosystem. That also can be taken care by this membrane. As many people are also focusing on energy aspect of the osmotic computing, they want to minimize the energy in each and every layer. People have come up with a new type of solution that is called as energy aware osmotic computing. And here, if you look into this computing paradigm, or you can say osmotic computing ecosystem, the microservices can be categorized into three parts. One may be a general purpose microservices, another is network management microservices, another is security management microservices. So general purpose microservices is not intended to security. Okay, although it is providing security features, but it is not meant for only security. But when you go for security management microservices, it will provide you better features. For example, here you can see, okay, before that I'll tell you about the 5-tier ecosystem. So you can see these are the different devices that we are using. It may be a headphone, it may be an electric bulb with a sensor, it may be a smart home, smart watch, smart vehicle, it may be anything which we considered in IoT devices. So here we have micro data center. So this micro data center is having less capable in comparison to the cloud data center. Okay, and in each and every layer, like you can see here IoT devices, here edge computing, and here cloud computing layer. Okay, so in between two different layers, we have a osmotic layer. Okay, this is a osmotic layer between tier 1 to tier 2. Similarly, we have another osmotic layer between tier 2 to tier 3, right? So what actually the objective of these layer is that each layer is equipped with a OTM. OTM stands for osmotic task manager. So whenever a task wants to migrate from IoT layer to the edge layer, it is going to be requested to the OTM. OTM has to take a decision whether to execute in, let's say, this edge micro center or this micrometer, or there may be numerous micro data centers are available in this layer. So it has to take a decision which micro center data center is capable to execute that particular task. And the main objective here is to improve the throughput. We'll see how much task we can execute for a time unit. We can also look into the cost incurred to execute the task, and what is the response time. Sometimes the closest data center will give you a worst response time in comparison to a farthest data center, right? So response time is also one of the important factors that we can consider. And in layer 2, you can see that is our edge layer. We can do some kind of filtering operation. We can do aggregation. And suppose a sensor is keep on sending the data, we can find average, minimum, maximum. We can use different type of gateways. We can go for router, we can go for switch, we can go for bridge, gateway, other things, right? Or you can use Raspberry Pi kit or Arduino kit. They can also be there in the edge layer. So the data is going to be forwarded from IoT to the edge, then edge to the cloud layer. Yes, here you can see different type of microservices. Like if you look into three different type of microservices, as I already mentioned, MS stands for MS stands for microservices. MSNet is specially for network management, and MSSCC stands for microservice security management. So in the edge layer, you have different micro data centers. So here I considered three different micro centers. You can see in each and every micro center, we have general purpose microservices. And one microservices, general purpose microservices, is connected to another microservices through the network management. Right? Means one unit is connected to another unit through a particular network. Like here you can see MS is connected to MSNet, which is present in the edge layer, and edge layer MSNet is connected to a cloud layer MSNet, and that corresponding MSNet will connect to the general purpose microservices. But the security requirement is a special requirement if it is required to a particular system. Like here you can see this particular cloud data center is providing you microservices with security, or you can say microservices for security management. However, this particular cloud data center is not providing microservice for security management. So like that, it will be different. So it is different, okay? Like here you can see also, like in the edge layer, this particular part is not supporting you the security features, whereas the other two provides the security features. So this is all about osmotic computing ecosystem. If you want to work in osmotic computing field, there are numerous of applications we have. Many people have worked in healthcare. Many people also applied the blockchain with osmotic so that we can provide a transparent system without tampering or tamper-proof system. Many people also used osmotic computing for industrial IoT. Many people also used in the micro element orchestration and networking, and so on. There are different applications are there. So in this slide, I have also given you over a different year, starting from 17 to 2020, the paper published in the different areas that you can look. If it is matching with your area, you can read more about the osmotic computing to implement in your respective domain. Now the second part is, here I want to show you a simple task mapping algorithm. So in this mapping algorithm, we have two different categorization. As I already mentioned, we need task level categorization. Also, we need processing level categorization. And also, I have told you about osmotic task manager between the cloud layer and edge layer and IoT layer. So what actually task level categorization do? Whenever a task is generated by the digital devices, the task is placed in a queue. Like here you can see the data generated by a smart electric bulb or by a patient data, or it is by a smartphone. They are queued in a queue. All the tasks are put based upon their generation, based upon their arrival. It will be stored in the queue. Once it is placed in the queue, then what we are going to do, we have to make the task level categorization. So what actually task level categorization would do? It is going to segregate the task into different type of categories. Like here you can see, I have mentioned the task level categorization into three different parts. One is ultra microservices, another is microservices and macroservices. So if your requirement is more, then the task is going to be classified as a macro service. But if it is in between a particular threshold tau 1 to tau 2, then it will be considered as a microservices. Even if it is less than tau 1, then it will be considered as a ultra microservices. So you can see here, actually the main idea is that ultra microservices can be taken care by IoT layer, where microservices can be taken by edge or you can say fog layer, whereas macroservices can be sent to the cloud. That is the main intention of doing the task level categorization. Once task level categorization is done, then we are doing the processing level categorization. In processing level categorization, first we will target to the those tasks are ultra microservices will execute using IoT processors. And if they are executed in microservices, then we can go for edge layer. And if it is classified as macroservices, then we can directly send to the cloud. However, if there is a delay observed in the IoT processors, then that particular task can be migrated to the edge. And if it is further delayed, it can be migrated to the cloud. So this is the algorithm. The algorithm is very simple. So we have to find the resource requirement for each and every task. If resource requirement is less than tau 1, it is considered as a ultra microservice. And if it is between the tau 1 to tau 2, it is considered as a microservice. And if it is above tau 2, we are considering that as a macroservice task. And the requirement of a resource can be determined by taking the task size and the minimum task size as well as the maximum task size. So here, for a simplicity of illustration, we consider the minimum size of the task is 0 and maximum size of the task is 5,000. But these are just, we have taken a random threshold. So in order to calculate the resource requirement and in order to show the illustration actually how actually osmotic computing finds the resource requirement of each and every task. Okay, so here you can see, suppose the task T1 is having size 1600. Okay, it may be in MB, it may be in GB, it may be in any value. So the minimum task requirement, let's say it is 0, maximum is it is 5,000. So 1600 divided minus 0 divided by 5,000 minus 0 multiplied by 100. So the task requirement is of T1 is 32%. When it is 4200, again you can calculate 4200 minus 0 divided by 5,000. Okay, 5,000 is the maximum and 0 is the minimum. So you will get the resource requirement is 84, right? And if I take the threshold as 30% and 70% respectively, 32 is above 30% but below 70%. That's why it is classified as microservice. And if the value is greater than 70%, it is classified as a macroservice. And if it is below 30, like here you can see, then that is considered as ultra microservices. Okay. So in this way, actually, we are doing the task level categorization. Then we perform the processing level categorization. So if execution time is less than tau 4, then it can be migrated to the IoT devices because IoT devices is capable to execute it. But if it is above, let's say it is not capable to handle by IoT devices, but the execution time plus tau 1, which is the, you can say the latency between IoT and edge device, which is less than equal to tau 3, then we can migrate into micro data center. Micro data center means you can run in the edge layer. But still edge layer is, if it is not sufficient, then you can execute it into the cloud data center. But in this case, you have to pay the latency between the IoT and edge and latency between the edge and cloud. So in this way, we are dividing the task process into 3 parts: IoT, edge and cloud. Now, in order to calculate this execution time is nothing but the task size divided by the resource size, right? Suppose the task size is 1000 and the resource size is 2000, then it is coming as 0.5. So for an example here, you can see I have taken 10 different tasks. Already I mentioned that how to categorize into microservices, macroservices, ultra microservices. However, let's say these 10 tasks we want to map into 6 different resources. Okay, 10 different tasks you want to map to 6 different resources. But if you look into here, as you have make a categorization, first if you take macro services, T2 is macro services, T9 is macro services, T10 is macro services. So I placed here, these three are macro services. Then we'll look into microservices. T1 is microservice, T3 is microservice, and T7 is microservice. So these are the service, and rest are called as your ultra micro service. So you can see is the service T2, T9, T10, they are macro service. So they will be executed in the cloud. Like resource R1, R2 is there in the cloud. Let's say resource R3 and R4 is there in the edge. R5 and R6 is there in the IoT. So these tasks are, you can say they are very large tasks, and the cloud requirement is also more. So you can execute T2, T9, T10 in cloud. However, if you come to T1, T3, T7, they need to be executed in R3 and R4, subjected to their time requirements should not be exceed a threshold of 200. Okay, like here you can see all values are below 200, then they are satisfying the request. However, you can see ultra microservice when you map with IoT processors, you are finding values more than 200. So if the threshold is 100 or 200, some resources are violating the threshold. In that case, such tasks need to be migrated to the edge. Okay. So if it is checked with edge, all the values are below 200. So these two tasks, that is T4, T5, as the values are more than 100. Okay. And you don't have any option. So in that case, these two tasks can be executed in the edge layer, not in the IoT layer. Right? Like that, we are managing different type of tasks in the different set of layers. So as a conclusion, I will tell you that the integration of these three different paradigms is really very challenging, and taking a decision that which layer is appropriate for real-time task is challenging, right? That can be solved in the osmotic computing. So osmotic computing provides a easy migration process, right? Not necessarily that entire ecosystems are belongs to only one provider. Okay, one cloud service, one is handling cloud layer, another is handling fog layer, another is maybe edge or IoT layer. So they need to collaborate. So in that case, the agreement between these providers is also very much challenging. So in order to be focused on the business opportunities, all these providers need to agree with a common terms and conditions. And the problem with this osmotic computing that if you want to work, there is no real-time data sets are there. So you have to generate your data sets, like I mentioned, some simple data which is generated through an example, right? That type of data you have to generate and test your algorithms. And if you are interested to learn more about it, you can refer to the first research article, which I have explained in this lecture, which is published in ACM Transaction on Internet of Things, that you can read if you want to know more about osmotic computing. And second paper is also belongs to osmotic computing, that is also you can focus. And rest are the cloud or IoT publications. And these are some of the references that you can go through. Yeah, thank you everyone. If you have any questions, you can ask.
Sir, since we are streaming this on the YouTube channel, so
Yeah.
Most of our participants are on the YouTube channel, so they have posted the questions,
Yes.
which I have copied and posted here on the
Chat box. Yes. Yes.
chat box. So,
Yeah,
so
yeah.
you can you see the questions?
Yes, yes, yes. I have seen some questions. How osmotic is beneficial to society? Okay, there is a good question, right? Because there are many applications we have, like I mentioned, healthcare applications where you need immediate actions, right? Like as I mentioned, suppose you are capturing a reading, let's say blood pressure, or you can say SpO2 of a particular patient, and it is deviating a particular range. So immediately you need to inform to the healthcare professions, right? So in such applications, osmotic computing is really essential. Every time you should not depend on the cloud, right? So that may be one of the societal applications where you can solve the issues of latency intensive applications. Okay, where latency, if there is more delay, which will lead to a big effect, such type of things you want to avoid, there you can use osmotic computing. So in that way, it is helpful to society. Next is how this osmotic computing help in microservices. Yeah, microservices, as I mentioned, you can see that when you are moving from one layer to another layer, lot of tasks are involved. Like migration is not only the task, it is one of the important tasks when you want to move from one layer to another layer. Apart from migrations, also you can see deployment of the services, managing of the service, controlling of the service, decision making of the service. These all are associated to make a decision, right? Sometimes you can decide that no, agent fog layer is also not capable to execute it. It should be directly sent to the cloud because it's a large task, right? So in such a case, you can see that you can decompose this into different microservices. You can treat these as different microservices. Migration is one of the service, security requirement is one of the microservice, or network management is one of the microservice. So that combinedly you can take a decision. So in that case, we treat each and every one as a microservice. So in that way, osmotic computing help in the microservices. In fact, all the functionality provided by osmotic computing, they are in the form of microservices. Then another question somebody asked about, this process level categorization will help in efficiently utilize different resources. However, setting the optimal time to categorize them will be difficult. So processing level categorization will help in efficiently utilize, obviously, because if you categorize into different part, as you are dividing the task, you are dividing the resources. So the number of mappings between the task and resources is going to be reduced. For example, large task is there, then definitely you have to go for cloud. If it is a very short running task, you will go for IoT. So this categorization is really helpful you for better utilization of the resources. The second part you have written, however, setting the optimal time to categorize them will be difficult. Obviously, that's why I told you, setting this threshold I mentioned as tau 1, tau 2, tau 3, and I have assumed some values to show you that how actually this processing is done. But practical case, it is very, very difficult, right? That is obviously finding the optimal time is very, very difficult. It is only dependent on the simulations. If you run a simulation with different threshold, then only you can suggest that yes, this particular threshold is beneficial. Yeah, you are asking, somebody is asking about some research areas. I mentioned 4 different research area in one of the slide. So that is related to service heterogeneity, service migration, or that is one is seamless collocation of cloud and edge for my service migration. So whenever you are migrating one layer to another layer, migration is fine, but you have to see that like migration case, we say that there is a hot migration, there is a cold migration. So cold migration case, there is a interruption. Okay, but hot migration case, there is no interruption. So if suddenly you are moving from one layer to another layer, the service discontinuity should not be there, right? So seamless co-location of the service migration is one of the research area. Reduction of the latency and energy consumption, like many people nowadays focus on energy efficient cloud osmotic computing, that may be one of the research area. And controlling and managing of service heterogeneity, that also you can look at how to manage, how to develop a better osmotic task manager, which can help to take a proper decision on moving of one layer to another layer. That can be considered as one of the research area. Okay,
Okay, sir. No other questions in the chat box so far we see here. So with
okay, you
that,
can share my email ID if they have any
okay,
questions, and they
certainly,
can
sir.
write to me. And I'll also share my presentation with you, sir.
Okay,
So
sir.
you can share with the participant. So
Okay,
later
sir.
point
Okay,
of
sir.
time, if they have question, they'll
Thank
ask me.
you. Okay. Okay, so on behalf of the organizing committee, I convey my deep regards and hearty thanks to our speaker, Dr. Sanjay Kumar Panda, for providing a practical exposure to effective smart systems, tools, and related applications in the field of osmotic computing. So, sir, will be glad to present you a small token of appreciation, a certificate.
Yeah, thank
Uh,
you.
Sir, will be presenting it to you. Sir, is it visible?
Yes, sir, it is coming now.
So thank you, and once again, sir, and thank you all the participants.
Yeah,
Sorry,
thank you, everyone.
sorry, sir. Uh, so with that, we come to the end of the day 2 session, and we'll join tomorrow again at the same time, 3 p.m. with so thank you.